Okay, so I have one caveat I have to mention right up front, and that is that my computer died before the show was finished. And so I have, some of these slides have no annotations on them. I'll try and remember what I was going to say anyway. But I also should have acknowledged Murthy here, because he's been badgering me with this question of what do we really know is present on Europa? You know, and I think that's a good question.
We need to ask.
Yeah, exactly. So this is going to be a little bit of a tutorial, and a lot of people in the room have already seen some of this. There's some things here that nobody in the room has seen, I guarantee it. But I'm going to try and introduce geology to this, because we have spectroscopists don't always know a lot about geology. And I think that there's a real good synergy that comes together when you can actually associate your spectra with individual geologic exposures on a surface. And I know some of you may know I was with the NIMS team starting in 1993 or so. So I was science coordinator for Europa. And since that time, published a bunch of papers on this with Brad Dalton and a bunch of other folks. So, but basically the subtitle here is, you know, geology and the radiation environment. Now there's going to be a whole section on the radiation environment. I think it's tomorrow. And so I'm not going to beat it to death, but this, in 2013, Brad and I got together with Tim Cassidy, and he generated a number of radiation environment models for Europa. And we used them to do some correlations. I'm going to show those, but what this is I think this is electron energy. It might be, I should see again, I missed that annotation. So, but anyway, bear with me. So we're going to talk about geology and radiation environment. Now, this is showing the locations of most of the observations I'm going to talk about. We have something right at the trailing apex. We've got something at the leading side, trailing side boundary. We've got a few other guys scattered around at higher latitudes. And we have one way around here on the leading side. So we've got a pretty good geographic distribution. Now from these, we were able to extract 55 individual, unique, non-overlapping spectra. So they're pretty much the basis of this talk. So one thing I should also say is that this work is based on linear mixture modeling, which Brad Dalton kind of really got some traction with, starting about 2007. What this shows is the non-ice cryogenic spectra for a variety of hydrated compounds, and there's the sulfuric acids in here, and the magnesium sulfates are in here, and three little frozen brine samples. We got reference spectra for water ice of various grain sizes. This is just a small sampling of those, but what you probably all know is that the smaller grain sizes are more reflective, and the largest grain size starts to get really dark down here in these absorption features. Here's an example of a fit where we're deriving a composition based on a NIM spectrum, which is the circles. This is a ridge plains exposure, which is basically a pretty small area. I'll show it. I'll show a map view later. Again, what we find here is that 46% of this is accounted for by water ice at 100 micron grains. So the linear, actually, Mike showed some linear combination work too. So it's, the caveat, of course, as Roger knows, is that we don't go out over here. But at the same time, there's the strength of these water bands really helps us distinguish between things. So What else about this? I don't think I need to go any further on this at the moment. And the alternative compositional modeling approach is radiative transfer modeling or intimate mixture modeling. And from Roger's famous work here, we find that if you mix a very fine-grained dark stuff with a bright compound, a linear combination of the two does not provide an accurate representation of the spectrum. And what's happened here, jarosite and allanite, the linear combination has a reflectance up here in this part of the spectrum from 0.5 to 1.5, but the actual measured reflectance is down here, and that's because the smaller dark particles have disproportionate influence on the radiative transfer processes. So this is a case when linear mixture modeling is not going to do the job. So to see whether what we also can call that volume scattering, that effect, to see whether that has a significant impact on our investigations of Europa, we recently did this comparison study where we took this identical spectra, analyzed them with radiative transfer models and with the linear mixture models. And what we found was that we couldn't, basically we got slightly better fits with mixture models with a few salts in them, but we got better than 98% correlations between the radiative transfer solutions for water ice and for hydrated sulfuric acid. And those were the combinations that Bob Carlson modeled. And we reproduced them really well. So this paper's out there if you want to go find it, or if you don't. Okay, enough on the methods. Why, Murphy, why do we think there's water on Europa? Well, this is a 1966 paper, and there's a suggestion down here. The records of Europa and telescopic observations characteristic of the reflection species of spectrum of a snow cover. And I think this is 72, Pilcher et al. In Science, they got water frost absorptions in Ganymede, J2. So this is their spectrum, and you see the absorption feed. Actually, this is wavelength is running in this direction. So this is the 1.5. This is 2 micron feature. 1.65 shows up pretty good. They felt that they could conclude fairly conclusively that water is on Europa. Okay, so now since then, I think that conclusion's been repeated maybe in the hundreds of times. I don't know, a lot of times. This is a fit that Brad Dalton produced for this leading side. This is 100 west and 5 or 10 above the equator, and we get 83% water ice abundance in this. The model is returning 67% 50 micron and 15% 75 micron water ice. There's a minor salt mirabolite component to this, and I put here again our reference spectra for water ice, and you can see, I mean, they really agree pretty well. So okay, so we'll come back to a little bit more on the ice later, but now I'm going to shift to something else that I think is pretty well supported. And that is, why do we think there's hydrated sulfuric acid? Now this is actually the sulfur flux coming out of Tim Cassidy's model, and it's in 10 to the 7 ions per square centimeter per second. So the conclusion I wanted to take out of this is that there's a chemical feedstock blasting in a blizzard onto the backside of this object. So this is one of the, and again, I don't have the annotation, but I wanted to make a couple of points. Strazula lab work showing you can produce the sulfuric acid by implantation and radiation. So here is another contributing set of observations. This is from right at the trailing apex for independent spectra with the error bars we get. This is from the Europa or NIMS G1 orbit, but every one of these things has got 60+% sulfuric acid abundance. And I think it's consistent with telescopic observations like we heard this morning, and others that weren't discussed. And I think it's consistent with Bob Carlson's sulfur cycle model, which he was able to replicate the NIM spectra fairly well using only water ice and hydrated sulfuric acid. So there's this kind of confirming information. But I think then maybe, I'm not sure that this paper, 2013 paper by Dalton et al. In Planetary and Space Science has really gotten much attention, but basically with the radiation models and linear mixture modeling, we really have two independent models going here. There's no feedback between our mixture modeling and Tim's radiation models and Tim's. So, and again, what we have over here is the sulfur flux, and what we have over here is the electron energy. And as I said before, we got 55 spectra from all across the longitude range on Europa to take a look at. And in that paper, we show this correlation. And what we're showing here is the sulfur ions and sulfuric acid concentration. And what we have up here is the trailing apex with the highest acid. This followed by this little guy over here. And then these guys down here show this cluster. And then around the back side, we have these other two observations where we got very low acid abundances, like 10% or 5% or 0 from those solutions. And you see a pretty good correlation here with the sulfur ion flux with the acid abundance out of this modeling using all of these non-overlapping spectra. Now, we get a slightly different picture with the electron energy, and it's got some interesting differences, but they're actually kind of cool. You see, actually the trailing apex in Tim's electron energy model is getting a little bit less energy input than we're receiving over here at this 14 SUCOMP 3 observation. So basically, either this, you can consider this one to be off the trend here, or you can consider this one to be off the trend here. But what I get out of this is that the sulfuric acid hydrate abundance looks to be jointly controlled by the sulfur flux and by the energy, by the electron energy. We also looked at the total energy. Okay, we didn't see that. We also, Tim did ion energy separately. We did a fairly comprehensive modeling job on this. And this, again, I'm interpreting this as confirmation of both. Basically, the sulfuric acid hydrate abundance tends to confirm the structures on the radiation model, and the radiation model tends to confirm the adequacy of linear mixture modeling in terms of representing sulfuric acid on Europa. So this is like, oh geez, great. Yeah. All right, so I think this is a strong result that's not generally appreciated. And from this, my opinion, Murthy, is that I'm pretty darn sure that sulfuric acid hydrate exists on the surface of Europa, predominantly on the trailing side. Okay, so. Okay, now as a side benefit of our modeling, the linear mixture modeling reproduces grains or extracts ice grain sizes and abundances at the same time. Back in, what is this, 1984? 83, this guy, Roger Clark, came to the conclusion that if you irradiate clusters of icy surfaces, that you would end up preferentially retaining larger grained ice. And I think it, correct me if I'm wrong, but basically what happens is that the finer grained stuff gets destroyed and the median of the sample goes toward the larger grains. Okay, so we can look at this with our linear mixture modeling and Tim's sputtering model. So this is a separate paper that Tim led, and what we get, we've got water ice grain size up to a millimeter, and the sputtering rate coming out of his model, and the locations where our points are derived, and we get a correlation of 0.98 of the prediction out of the sputtering model and the water ice grain size. I like it, okay? There's caveats. There's no amorphous ice in our mixture model. There's no submicron ice to mess with that, if that could be relevant under these conditions, maybe especially on the leading side where it's so much finer grain. I don't know, but again, this one would be annotated. And here's just another, basically, I consider this a confirmation of the melding of the linear mixture modeling and the radiation environment. So now, okay. Okay, that's good to know. I was going to ask you that at this conference, so offline. Anyway, I'm not sure where the time is, but I'm going to flip now from sort of global view to more local study. And this one is one that, unfortunately, my collaborator, Brad, had to terminate his career rather abruptly due to medical reasons. So this thing never got published, but it turns out that in the C3 orbit, the NIMS instrument was serendipitously able to image this Mannanan impact crater, which is here. What we've done here is we've registered and sandwiched the NIMS data as a false color on top of the SSI imaging data. And the light blue color is more icy. Is representing the highest abundances of water ice, and that it's even though it's not super clear that there are rays coming from this crater on Europa in the imaging data, it's pretty clear in the NIMS data that there are. These colors are much more heavily hydrated, and we'll get to what that may be. Okay, and this is, I think, Bellis linea. Right here, goes way out, way around. Anyway, okay, so in this case, collaborator Dr. Louise Proctor was able to generate this really amazing geologic map, right? So we have a number of geologic units. Again, this was 4 to 6 kilometers per pixel resolution. So there's areas, the knobby terrain, for instance, that are sort of not in the best resolution, but in general, this is an interesting thing. So what we can do with the NIMS data at this resolution is we can extract spectra from the crater floor, from the immediate ejecta blanket, from the knobby terrain, from the various units, and we did that. We pulled 40 different spectra out of this observation, and what we got, I actually got this one annotated, is that the acid hydrate abundance in Mannanan is about 18% lower in the crater than it is going out along the rays and into the background acid abundance we obtain, which is about 61%. So what you've got here is you've got a dimple or a dip in the abundance of the sulfuric acid hydrate associated with the ejecta blanket of this crater. And you can actually see that right there, that little green finger going into Bob Carlson's acid hydrate map. So what this offers the possibility of is that you might be able to age date If you had a gardening model and a radiation model, and you could predict the input to and the production of the rate of production of sulfuric acid hydrate, and you got this deficit, you might be able to say, well, this has to be between X and Y million years old, or 100,000. So this is something that actually can be observed from orbit in Clipper and possibly inform Clipper's choice of targets in later orbits. Cool stuff. All right, now, Carl and some of the folks in this room were in this history too, and we're all going to have different points of view on it. But I just wanted to, now we're going to talk about the non-ice, non-sulfuric acid component on Europa's surface for the rest of this talk. So basically in the late 90s, when we first started getting the NIMS data, they were saying, okay, well, we've got icy places and we've got non-icy places. We don't really know what the non-icy stuff is, so we're going to call it the dark end member or the non-ice end member. And so this is the Puil crater in imaging and NIMS with the non-ice extreme here at the red color. And pretty similar thing. This is from Tom McCord's 1998 science paper. And the, what's he calling it? Non-ice and ice-rich components of the surface, okay? So that's step one in our understanding of the composition, if you don't count Voyager and Soderblom and Uchida and those people. And then we got into this very interesting conflict because Tom McCord went and said, this is salts, and Bob Carlson came along and said, wait a minute, you can describe it with sulfuric acid. Okay, so they put out sort of competing papers, 2000 to 2004 or 5 that were, kind of more and more antagonistic. But it remained an open question. I think it still may be an open question to some folks in this room. But in about 2005 to 2007, we had Tom Orlando's lab work and Brad Dalton's initial linear mixture modeling work, finding that basically if you use both, if you allow both components in your model, you get a better fit to the NIMS data. Significantly better fit. We tested the crap out of it in this paper here, and we found the same thing. Basically that if you just use ice and water or you just use salts and water, you don't get the kind of fit over this range that we're looking at. So now, when people, when I read in papers that, oh, well, there's still a controversy between, salts and acid, I think that was kind of in the past. Other people, you can argue it. I know you might argue it. All right, jumping to another high-resolution observation. I'm going to try and go quick here. Again, we have the false color NIMS data superimposed on the SSI background. We're down here. We got a geologic map from Louise. This has got a really nice diversity. These green things are low albedo plains. They look like the youngest stuff there. They look like they were extruded on the surface. They embay surrounding terrain and ridges. The oldest, most beat up radiation heavy crap is this these ridge plains, all the gray. And so every one of these locations corresponds to a spectrum, a separate spectrum we extracted. So we had 40-something spectra to compare. And the consistency coming out of the linear mixture modeling, if I take, wrong button. If I take 2 of these R14s, just compare the spectra without doing anything else, say they look amazingly consistent. Same for the other units. So, but now here's something else, all right? People used to say, well, the non-ice material on Europa is the same everywhere, all right? It's the same everywhere. But they could still see like these differences in the strength of the absorptions and the distortion of the water ice bands, right? So what we did, just for fun, we had one exposure of chaos in this area. We had low albedo plains that I was talking about, and some of the ridge plains, the really light stuff. So the ridge plains is the deepest water ice absorption. The chaos is intermediate, which you might expect if you're looking at Connemara chaos and those tilted ice blocks that are floating in the muck. And the most distorted water ice bands are for the low albedo plains. So we model them with a linear mixture model and we get abundances. Sulfuric acid hydrate's not that different, but we get much higher abundances of the bloodite and actually the magnesium sulfate brine over here. And the total, I'll just show it. Oops, maybe I left that slide out. Anyway, what it amounts to is that the ridge plains are dominated by water ice and sulfuric acid hydrate. This accounts for 80%. 10% hexahydrite, which is not that different from epsomite, 6 waters instead of 7. You get increasing abundance of the mirabolite and the bloodite components. These are salts from the library as you go to the progressively more distorted water bands here. Okay, now you can also do tectonics with this stuff. This is Louise had a paper, 2016, looking at the bands only. And I know there's another paper in this conference about the bands too. So, so we were able to extract spectra from gray band. There's again 20 different exposures, and I just took these because I could to see if there was any gradation in the gray materials, and these two from the dark band. And we find, on the basis of composition only, that the gray bands have higher abundance of water ice, or of large grain water ice, and also less of this hydrated salt component, the mirabolite and the magnesium sulfate brine. So, and traditionally, the gray bands have been interpreted stratigraphically as older than the dark bands. And then we have the anomaly here. So what's going on here? We've got a gray band that's contiguous with a dark band. And the idea is, how do you explain that? Well, it turns out Paul Shank's worked and shown some crop circles not too far away. And it appears very reasonable that there is a scarp that's formed along that boundary, right along that boundary. And so we're hypothesizing that how do you resurface this with newer materials? You can have this attachment fault model and either sills or diapirs, and end up with extrusion on the surface of fresh, young material from within the crust. And one of the cool things that is not noted here, I'm almost done, I think, is that the composition we obtain from this fresh, hypothetically, more freshly emplaced non-ice material is that it's very similar, almost identical to that of those low albedo plains, which we're going to get to here. Forgive me if I'm running over, but all right. Now we're at the smaller scale. Before we showed with Mononon that, perfect, okay, with Mononon, you had this dimple in the sulfuric acid abundance associated with that crater. Well, we're finding kind of the same thing, but it's now, instead, it's an association with this little patch of slurry, of relatively low topography, hypothetically cryovolcanically extruded material. Okay, this is the low albedo plains 1D. This is the R2. Here are stack plots that are showing the compositions. Here's this, we saw this before. This is like 50% water ice in the ridge plains, but at the same longitude, and maybe, I don't know, 50 kilometers away, we get a distribution that looks like this with absolutely no water ice. Our model is using no water ice to fit this. 20% mirabolite, bloodite, and magnesium sulfate brine as the most significant component. Very different stuff. The spectra look that different, but they're different stuff. And down here we've got we're seeing this gradient because the sulfuric acid hydrate abundance decreases as you move from the trailing side apex around to the leading side. And this is exactly what's shown going across the trailing and leading side boundary here, is that for these units, these exposures, the acid abundance is on this fairly reasonable, nice trend. But what's weird is down here, you've got this group from right around this area that are like 30% below what you would expect based on that gradient. So what that says to me is that this stuff might have been in place relatively recently, and the radiation environment has not had time to bring that surface into equilibrium in terms of production and destruction of sulfuric acid on this surface at this longitude. This is another thing you could look at, you could look for with the clipper. Okay, this is just for fun. Nobody's imaged this. This is fairly near the leading side apex. But we thought we had a crater, and I showed this a couple years ago at AGU, and we see these absorption features that we don't see anywhere else, 221, 235, 225, 233. In this ring portion, and we also took a spectrum from the very center of the crater area, and from Rogers Library, we get a bunch of candidate phyllosilicates, and the chlorite up here looks like a pretty good match, you know, to that outer ring material. The center spectrum is not as well matched by any of these options. But so, how do you get this stuff? Right, you have what looks like a crater. We should verify this when Clipper gets there. Is it a crater? Is it something else? But you can actually find comets and asteroids with the proper compositions to deposit the chlorite stuff we see. Okay, second to last. This is the NIMS observations that have resolutions of 10 kilometers per pixel or smaller. Right now, Mike Malaska at JPL is leading a PDART program to reprocess the highest quality NIMS observations and put them in forms that can be used by modern investigators, including ArcGIS. And so instead of the NIMS data being completely inaccessible because of the huge difficulties of working with it, we're going to make it so that anybody can download it from PDS and go to work on it. And in that same light, if anybody here wants to get their hands on those 55 published Europa spectra for individual units on the surface, I'm happy to supply them. So just give me an email. And that's it.
Great. Thank you, Jim.
I have a quick question.
Mm-hmm.
Like those 55 spectra, did you extract them all the way out to 5 microns?
Yeah.
Great.
We didn't analyze them with the mixture model, but a lot of them still have that information. Yeah.
Right. And my comment was on the mixture modeling, when you limit the spectral range so the absorption bands are similar strength, you can throw all kinds of stuff in there, and as you expand your wavelength range, especially out to the 3 microns, you'll find the salts, just their abundances have to drop because they won't fit.
I have no axe to grind here. I don't think it's chlorides. I don't think it's sulfates. It is what it is. We need to find out what it is, you know. So,
Hi.
Thank you.
Yeah. Quick question, I hope. Every couple of years I hear about the NIMS data being recalibrated, and then a couple of years later, recalibrated yet again. How robust do you think some of these earlier conclusions about the spectral interpretation are in light of that? And maybe it's not an issue. Maybe they're pretty firm and stuff. But
okay, well,
there's
something takes a couple minutes to answer that, and I could do that offline if it's necessary. But let me just say. The NIMS stepping motor was apparently damaged by radiation, and so the step sizes changed. And the start position for the grading was slightly variable. I think probably due to the radiation also. So in 1999 or 2000, there's a paper with Tom McCord and me that talks about the recalibration of the NIMS data. And basically, the spectral coverage of each detector increased by about 15 to 18% over the course of the mission. So instead of starting at 0.69, it would start at 0.68, and ending at 0.8, it would end at 0.83 for the first detector, say, just off the top of my head. That's been compensated for in all the new stuff we're doing. It's also been compensated in all the spectra I showed you. There's been calibration studies using the 1.65 micron band, which is fairly sensitive indicator, but is still wide enough to see with the NIMS spectral spacing, channel spacing. So I really don't think there's an issue there, and especially not with these large-scale conclusions. I mean, but the best data will be coming out from this PDART in a year or two, I hope.
So I want to ask
Bob?
a question. You showed that these things that Paul showed, scarps or whatever they're called, legends slipping out, and then fresh material flowed out onto them. And you use the sulfur implantation rate as a time scale? Oh, thank you.
No, that's a hypothesis to be tested.
Oh, okay. I mean,
That's-
those rates are known, and
You would think
and
so.
the geological timescales are known.
Well, I'm not
It
sure
hasn't been-
they're known so well. Didn't Bob Carlson's paper, I think in 2005, say all the molecules in the sensible surface are modified in 200 years or something?
I should know the answer because I was an author. But
Yeah. I mean, if it's that fast, if it's truly that fast, then yeah, that makes this potentially more powerful means of assessing that.
more powerful or less likely? I mean, I thought
Well, yeah,
What,
I mean,
what are the timescales for those processes,
well,
Paul?
but the Bananon crater that we showed first, that's not as fresh and young. I mean, the freshest, youngest thing is the Puel crater, right, with these beautiful extending rays. Bananon is intermediate in age, probably, and you have like a Tyramacula that's old and degraded, right? We haven't done Tyramacula yet, but because Bananon is intermediate in age and still shows that deficit, I'm thinking that maybe there is scope to be able to do that, on reasonable timescales. But again,
I got it back here.
it's something for the future generation.
So I am incredibly envious of your high spatial resolution, but I'm not so envious of the low spectral resolution. My worry is that at that resolution, you can almost fit any spectral library if you have enough components and you're just trying to smooth stuff out. So my guess is that at higher spectral resolution, you would not be able to fit most of those components that are in there. So my question is, what is the resolution of Clipper? Does it have the same NIMS resolution, or are we going to be stuck with the same low resolution? Nobody's going to know the answer.
I can answer that. It has a resolution of 10 nanometers and sampling of 10 nanometers.
What is that compared to NIMS?
So NIMS was 26, but it often didn't run at the full resolution because the downlink constraints actually subsampled it spectrally. So although the full width half max was 26, often the sampling was at 52. Is that correct?
Yeah, most of these are at 26.
Or 26 at 26?
Almost all of these are at 26, except the G1. The
Okay.
G1 was at half sampling.
So a factor
Yeah.
of a couple better?
3 times
3?
better. And that SNR is going to be exquisite, we predict, on MICE.
Yeah, and let me address a couple of things there. I really think that the fear, the innuendo, okay, that a lot of spectral components in your library can fit anything is not really applicable here, because all of these are, the reason that made Brad's library special is they're all measured at the cryogenic temperatures. I mean,
But it's a question of
that.
how many things you have in your library. If you have sulfates in your library, you'll fit sulfates.
Yeah, there's like a dozen, but there's also carbonates and I mean, you mentioned the source of the sodium, and from what these analyses are telling me, the mirabolite is successfully beat up and reduced in its abundance as you go from the leading to the trailing side, and maybe that's being broken down by the radiation. I think that's something that might want to be tested in the lab, see what happens if hydration, if waters of hydration are lost from mirabolite and sodium freed from that structure.
Yeah, so I guess my feeling is just that philosophically, if your goal is to reproduce a smooth spectrum, and to do it you have to take a library with a bunch of bumpy spectrum and add them together to make them smooth, it fits, but it's not a very satisfactory identification of these things. So in my head, there's basically no evidence for these sulfates on the surface. There's a model that can fit them, which is very different from saying that we have knowledge that there's a single sulfate on the surface.
Yeah, I'm not saying we have the knowledge that there are sulfates on the surface. I'm agnostic on that. I believe there might be chlorides. There might be something.
I wouldn't
else
say they're
entirely.
chlorides either. I say the same thing about about my identification.
But I having worked on these things hands on and seeing how hard and it's really not that easy to get the chi-square. Some of those have had iterations of the model in the tens of thousands, and Brad's technique was to say, okay, I got a fit here. Let's kick this out over here and try it again and see if we get, see if that was a local minimum in the hypersurface and we can get a better fit somewhere else. And the other thing I wanted to say was that this hydrated sulfuric acid and the water ice spectra are fairly smooth, and the lack of spectral resolution is not really going to affect those conclusions whatsoever.
Oh no, I think that those are good identifications. I think there's should be no question about sulfuric acid and water ice.
We looked at
it's just all that other stuff that's just very difficult to tell at that resolution.
Yeah, but I mean, the fine structure of changes due to temperature in bolidite or epsomite has been published, and there are spectral changes that occur going from 300 to 70 K. But when we look in the NIMS data for that, that's basically beyond our grasp, except to the extent that the large scale slopes and features of the spectra are controlling. And we're not, averaging things, basically. We're summing things. That was the point of those stack plots. It's not really smeared or smooth in any way.
So to summarize, I think you both are saying we need more laboratory data of more relevant minerals under the relevant temperature conditions, but also I would say irradiated minerals as well, because we are making a lot of detailed, I would say nuanced interpretations based off of specific shapes of these broad features that may not be diagnostic of composition, but may be diagnostic of crystallinity. And so we may be interpreting perchlorates or chlorates accurately, or maybe they're sulfates, but unless we irradiate them, maybe we'll find that there's a totally different mixture. I mean, when I see some of these models and these are low hydration minerals up there, I question even including that in the database, because we can, I'd say, fairly confidently assume everything should be highly hydrated there if that's physically possible for that mineral, whereas I do know that NaCl, right, you can't hydrate that too much. Right, there's just a certain amount of things. So, but combining geology as you do with composition, I think, is very powerful, right? Because we can take.
I recommend it for.
Absolutely,
Clipper,
right?
yeah.
And thermodynamics. Understand what minerals potentially we should be looking for, not add things like beryl and things like that we start. We know at least we're doing it right. These are cryogenic hydrated minerals, and we're merely arguing whether it's a chloride or chlorate or sulfate. So I don't think it's really that bad. If we could answer that, then we'd understand if that matches, and we would confirm your theory that the leading hemisphere is dominated by endogenic materials, salt or whatever.
A lot of ice there. A lot of ice there.
Oh yeah, sure. Ice is everywhere where it's not sprouted. But I mean, the interesting stuff. Ice is interesting, but the geologically interesting. I'll stop saying what's interesting and simply say the non-ice materials endogenic on the leading hemisphere, on the trailing hemisphere. That is a exogenic would be, I think, an important conclusion. I am not convinced that is true. I'm still wondering if the chilling hemisphere can simply be a lag deposit that is so irradiated that it looks like sulfuric acid, or all we're seeing is merely the irradiated endogenic material, and it happens to look like sulfuric acid, and it's not an exogenic source at all. So I am. It may still be hydrated sulfuric acid because that's a radiolytic product of highly irradiated stuff in the presence of water ice. But I think there's a lot to be still figured out.
So I think
Couldn't
Murthy
agree.
has one more question, then we'll open up to general discussion.
Yeah. First of all, thanks, Jim. It's really a very nice, summary. The striking thing that I really liked about is correlating sulfur ion fluxes with electron fluxes. That both of them show that these bands grow in intensity or follow the fluxes, whether you call them sulfuric acid hydrates or XYZ, it doesn't matter right now. And that's the fact, and that fact was very strongly, brought to the community here. The one thing I also realized is that the discussion between you and Mike is that while Mike has better spectral resolution, you have better spatial resolution. One thing that we need to keep in mind is you don't get one end product in any process that is continuously under radiation. You have several steps, okay, and the equilibrium processes. And so if you have sulfur, let's say we have sulfur there, and we think we know about it, and there should be several processes that are under equilibrium. So it's not necessarily only sulfuric acid hydrate or some magnesium, salt. So in that way, using some combination of material is not completely out of, let's say, out of the sky or whatever it is, but we need to be careful not to linear mix them, but also try to see whether under radiation they remain to be the same as we have them. So there's a lot more work to be done in order to talk about what is non-sulfuric acid hydrate material is. That's it. Thank you.